Welcome everyone, and thanks for joining me to talk about the Rust client. Just a point for future, don't ever try and compile Rust code while also running Zoom on your computer, because you might run into some resource troubles. So as Alex said, my name is Russ Cam. I work for Elastic, principal software engineer, work on the clients team, and I'm based out of Brisbane. And you can find me on Twitter at 4loop. So yeah, come say hi if you have questions about the Rust client or questions about the .NET client, which is one of the other things I work on. I'm more than happy to help people out. So let's kick this off. So if you're interested in getting started with the Rust client, the first place you're very likely to go is crates.io, which is the Rust package repository. So if you go and search for Elasticsearch there, you'll find it. And currently we're on 7.7.1 Alpha 1 version. And we'll just kind of run through how to get started with the client first of all. So in your cargo toml file, you take a dependency on Elasticsearch 7.7.1 Alpha 1. And the client itself is an async client. So all of the functions are asynchronous, and that asynchronicity there is built on top of Tokio. So in order to be able to use async main functions and async tests, you're going to need to take a dependency on Tokio there as well. And then there's a couple of other dependencies, serde and serde.json there. So if you want to be able to serialize types to JSON and receive JSON back with the client, you're very likely to want to take a dependency on those two things as well. So internally, the client does use serde and serde.json, but you're very likely to want to use serde traits and the serde.json macros in your own code to send requests and deserialized responses. And then your main method here, if you attribute it with Tokio main, because it's an async main function, and then your code is going to go inside of there. And as a simple kind of getting started experience there, this is how you would use the client. So the client does have a default implementation. So if you call Elasticsearch default, you'll get a client that can connect to an Elasticsearch cluster on localhost on port 9200. And then to make a request there, you call a function on the client there. So in this case, search. Each one of the API functions here takes a part. So in this case, it's search parts for search. And these specify the components of the URL to the API. So we're going to make a request here to the post index, and then we're going to send a body here, which is using that serde.json macro here to serialize what we see here into JSON and then send that as the request. And then at the end, we await it here, and that's going to return a result of a response or error. So if everything goes well, we'll get a response back. And as you might expect on a response from any client that's communicating with Elasticsearch, there are a few things that you're interested in. So the status code, and here we can read the response body as JSON. We specify we're going to read it into a serde.json value here. So just like an arbitrary JSON type. And then from there, we can read the took value, and we can enumerate over the hits array and read out all of the source documents. So that's a simple kind of way of getting started with the client. But what might be easier to kind of have a look at now is maybe actually have a look at some examples in code. So let me just pull this one across here. So this is the repository that I have here running locally. And if you were to pull it down and start having a look, there's a couple of projects in here. There's an API generator package, Elasticsearch package, which is where the client is, and YAML test runner. We'll talk about a few of those things in a little bit. But if you're interested in running some examples with the client, so underneath this Elasticsearch directory, there is an examples directory here. So following the conventions of a Rust package, or I should say like a cargo package, inside of this examples directory, these are completely isolated runnable examples here. So there's 4 examples here. This first one here is about bulk indexing questions and answers from the Stack Overflow data set. So I do have an XML file which I've downloaded from the Stack Exchange archive, which contains all of the question and answers on Stack Overflow. So this example here is able to take that XML file, stream all those questions and responses out of there, and index them into Elasticsearch using the Rust client. So if we were to just run this one, so I'm just going to need to bring up my terminal. So here we go. So yeah, if we want to run one of these examples, then we need to have Elasticsearch running. But then what we can do is we can do cargo run and then specify the project that we want to run, because there's a few projects in here. So we want to specify the Elasticsearch project and then specify the name of the example. Index questions answers, which is the name of the directory that we find this in. And then for this particular example, we need to pass it a path to where that posts XML file exists. So it's Stack Overflow posts XML, and let's say we only want to index 1,000 questions and answers, and if the index already exists, then delete it. So these are just some command line options here just to make this example easy to run. So if we run this one now, it's just going to compile that example, and then we should see some output here, which doesn't look very good. Okay, that's not what I expected. Let's have a look. Okay, for some reason I do not have Docker running, so let me just start that one up. So there are some scripts in this project to be able to easily start Docker. We're just going to take advantage of those. Start an Elasticsearch Docker instance. And so run Elasticsearch. So we're just going to run up an instance of Elasticsearch, and then our example, we'll try running our example again.
I suppose that this is all in the official GitHub repository, so people can just clone, share, and reproduce?
Exactly, yeah, exactly. So yeah, there are scripts, shell scripts in there and PowerShell scripts. So if you're running on Linux or Mac OS, you can use the shell scripts to start up an instance of Elasticsearch. So I did have an instance running. For some reason, it decided to disappear. So yeah, so it's running now. So if we just try and run that index questions and answers example again, we should see 1,000 questions and answers indexed now. So kind of the core of that example is here in this Stack Overflow Rust file here. So yeah, so we had 1,000 posts were indexed. So we have a post type that models both questions and answers. And then these are all the properties on a question. We have our answer, properties on an answer, reading the XML file there, deserializing or reading each one of those XML elements into either a question or an answer. And then finally, inside of index posts here, we can see that we use the bulk API here. We build up a body based on the slice of posts coming in. We build up a bunch of index operations, and then we send those with the client to Elasticsearch, and then we check to see if there are any errors, and go on from there. So the next example then that we can have a look at is actually searching those questions and answers. So again, this is another standalone example where you can pass in a search query string. So we can do cargo run, Elasticsearch, and then the name of the example. So search questions, and then we can try and search for Elasticsearch. Actually, let's just try without any input. So this is just going to go and search over those 1,000 questions and answers we just indexed. We can see here compressing, decompressing folders and files, what we're doing with the values coming back there. So let me just pull this down a little bit. So this is the search query that we're performing. So yeah, if someone has supplied some input, then we're going to use it in our query here. Otherwise, we're just going to do a term query against the question type, and performing a search request against our posts index. And then the response coming back. Again, we're deserializing that to a SERDY JSON value. And then what we're going to do is just enumerate over that hits array, and then map each one of the source SERDY JSON values to our question type that we have. And then for each one of those questions, we're just going to print it out to the command line, which is what we can see here. And we can see if we click on this one here, it does actually open up that question. So it does link to a real question there. Similarly, we can search across questions and answers here. So that just gives you an example there of, so rather than just filtering down to questions, we can search across questions and answers, and we can rely on SERDY JSON here to deserialize to this post type, which is an enum and has variants of question and answer, and let SERDY JSON take care of deserializing it either to a question or an answer for us. And then if it happens to be a question, printing out a bunch of details from the question, and if it happens to be an answer, printing out a bunch of details from the answer. That's kind of a very, very brief bunch of examples to go over. So you might be kind of wondering, why would we want to go ahead and write a Rust client? Well, it's fair to say that Rust is kind of gaining a lot of popularity out in the community, in the programming community, but also a fair bit of popularity here within Elastic. It has been voted, I think, the most favorite programming language for the last 5 years now on Stack Overflow. And there are a bunch of different companies that are really starting to invest quite heavily in the language. So Dropbox is quite a big proponent of Rust. So they've written a bunch of compression components that they use behind the scenes in Rust. And similarly, Microsoft is also exploring Rust for its kind of safe systems programming language qualities. So yeah, it's gaining a lot of traction out there, I think. And there have sort of historically been a couple of clients out there. So there's RSES, which is a REST API client with a strongly typed query DSL. So it models some of the queries that you can send to the search API. And there is also Elastic there, which is again another client where you can then specify freeform queries. But it's also fair to say that why would we sort of go ahead and write one? Well, it's the Rust programming language itself is moving quite fast, and async and await came in November, I think, or went stable in November in 1.3.9. At the moment, I don't think either of these community clients, they implement futures, so they support asynchronicity with futures, but they don't currently support with async await in Rust. So Rust is moving very fast. Elasticsearch obviously moves very fast. So it seemed like there was a pretty good time, now to have a look to see what a kind of a client, an official Rust client might kind of look like in the language. So I took some, as Alex kind of mentioned in the introduction, we have this notion of space-time at Elastic. So engineers have an opportunity to sort of go off and explore an idea. And I took some space-time to go and explore and to see how far I could get in writing a minimal kind of viable product for a Rust client as part of a space-time project. Kind of as a way to learn a bit more about Rust, the language itself, but also I think, just to kind of take some time out to do something else. So that this kind of project came out of that. So as I showed you in the IDE, there's kind of three packages to the client. So if you were to go and clone this on GitHub at Elasticsearch Rust, there are three kind of main packages in there. There's the API generator, Elasticsearch, which is where the client is itself, and there's a YAML test runner, and I'll talk briefly about what each one of these things are. So the Elasticsearch crate itself is where the client is and all the client code is and the functions for calling all of the different APIs in Elasticsearch. There's kind of a few building blocks to that client, which we'll talk about briefly now. These components here are, or these abstractions here are quite common across all of the official language clients. So they all have a notion of connection pools, connections, a transport to actually send the request, some way of building the requests, and some way of handling the responses. In this Rust client in particular, this is roughly how it kind of hangs together. I've taken some artistic liberties here in how I've represented stuff, but let me sort of talk you through how it all fits together. So inside of the client, there is a root client, which is the Elasticsearch type itself. And then there's also a collection of namespaced clients. So these namespaced clients are basically how the APIs for Elasticsearch are actually grouped, not only within the Elasticsearch code base, but also in the specifications and in the documentation. So the cat APIs, for example, all live together in a cat namespace client. The snapshot APIs all live together in a snapshot namespace client. And each one of those clients, whether it be the root client or the namespace client, has the functions on there that represent the APIs available within that namespace. And if you were to call one of those functions, you get back a builder. And that builder then allows you to define the request body for that API, the parts, which actually get passed as part of that function that returns a builder. The parts define the actual variable parts of the URL for the API and model the different variants for an API as well. And then the params define the valid query string parameters for that API. And then inside of the client, there's a transport. So the transport has a dependency on a connection pool, and a connection pool is simply a pool of connections that are connections to nodes within an Elasticsearch cluster. So transport asks the connection pool for a connection. It gets a connection back. The builder gets passed to the transport. The body gets serialized to the request stream, and internally a lower level HTTP client takes the URL from the connection, takes the builder, takes the relative path, builds a complete path to the API, serializes the parameters, and sends that to Elasticsearch. And then what comes back from Elasticsearch is a response type. So there's a few different types of connection pool within the client. Again, this is something that's common across all of the official clients. The simplest kind of connection pool that you might have is a connection pool that has a single connection in it to a single Elasticsearch instance, or maybe it's a connection to a load balancer that is in front of an Elasticsearch cluster. So the connection pool itself in the Rust client is a trait, allowing us to have different implementations of a connection pool. One of those implementations is the cloud connection pool, which is something that makes it easy for you to be able to create a connection to an Elasticsearch cluster that lives on Elastic Cloud. Within the Elastic Cloud console, when you spin up a cluster there, you get provided a cloud ID there. You can simply pass that cloud ID to a cloud connection pool, and it will construct a connection pool there for you to that particular instance. So the next part after connection pools and the different types of connection pool is the transport. Transport really just has one method on it, send, which takes all of the components that you might expect of a HTTP request, makes that request, and then returns a result of response or an error if a problem occurred. So transport there, if you ask for the default transport, then you're going to get a connection to localhost 9200, on over HTTP, not even HTTPS. So if you want kind of more control over authentication details, certificate validation, whether to use a proxy, whether you want to set global HTTP headers, that's where you'd want to use the transport builder. So the builder here takes a connection pool. So you new up an instance by passing it a connection pool, calling a bunch of chainable functions on there to define the properties of a transport, and then at the very end of it, call build, and you'll get a transport back. And then you pass that transport then simply to the Elasticsearch client to new up a new client. So that's transport. So the client itself, or the root client, I should say, here's an example of the kind of API methods that you would see on one of these clients. So this actual implementation is way bigger than would fit on this slide. So I've kind of cut it down to just showing you what search and bulk look like. So you new up an instance of an Elasticsearch client, you then call .bulk on there. So bulk expects to, so it gets a reference to the client, gets a reference to the client itself here. And then you pass it the parts, which are the parts of the API URL to define where that bulk request is actually going to go, whether it's going to specify a set of indices or whether it's not going to specify any indices at all. And then what ends up being returned from that is an instance of this bulk builder, which I will talk about in a second. So similarly for search, search takes the search parts and returns this search builder. So jumping back here, this search parts piece here, it models the different URL path parts of the search API. So search API can either look like this, /_search, or it can specify one or more indices, or it can specify one or more indices, and currently at least one or more types, although this is being deprecated. So these three different variants of the search API URL are modeled in this search parts enum value, and that's what is passed here to the search function. And then each one of these parts enums has a URL implementation that can then return you back the relative URL here built from the values that you pass to it. So in this way, the parts enums control the invariants for how to build the URL, and it actually becomes quite difficult for you to build an invalid URL for an API with the client because of this. That's one of the advantages of using the client over just using a HTTP client yourself. So just completing this this piece here. So this search builder there is what we're now looking at here. So this search builder gets a reference to the client passed to it, gets the parts passed to it, and then on that builder you have functions for being able to set all the query string parameters and being able to set the body. Now the body on the search API and on most APIs accept JSON, a JSON body. So they are generic over T, where T implements the SERDI serialized trait. So you can pass any type here that implements SERDI's serialized trait to the body. So this way you can use not only the SERDI JSON macro to define a SERDI JSON value, as I showed you in the example earlier, you can define your own types as well for the bodies if you want to model the requests that you're making more explicitly. So after on this search builder, after you've called all the methods, so they're all chainable function calls, after you've called all of those, you then call the terminal send function here, and that's actually going to initiate the request to Elasticsearch once you await it, because it's an async function. So yeah, so the builder structs there define the body and the query string parameters for an API. So they constrain you to not being able to pass invalid query string parameters. They follow the builder pattern in Rust. So there are a bunch of different builder patterns in Rust. These are mutating builders. So each method call to the builder actually returns a new instance of the builder mutated. Yeah, so the generic over B, which represents the body of that actual builder, and they're all clonable as well. So we've talked about the client, we've talked about connection pools, talked about the transport, we've talked about the builders, we've talked about sending a request. I kind of glossed over though this kind of body method here, which is actually the body for the API. We can see here that you pass in a T and it implements serialize, but it actually returns a search where the T ends up being wrapped in a JSON body of T. So what is this thing? So in the Rust client, there is another trait that represents the body of an API call. And you might be wondering, well, why do we need a trait, if everything's application JSON, if everything's a JSON request? Well, there are 3 or 4 APIs, 3 APIs, I believe, in Elasticsearch that actually can accept new line delimited JSON. So we come into a bit of trouble there when we're trying to represent uline delimited JSON if we constrained the API to only accepting like a SERDI JSON value or something that implements SERDI serialize. We also need to model these new line delimited APIs in some way, and this is where the body trait comes in. It allows us to model APIs, have APIs accept bodies in different formats. So that JSON body of T takes a T where the T implements SERDI serialize, and then it will use SERDI JSON to write that to a byte buffer, and that byte buffer will be written to the request stream. But as I did also mention, there are 3 APIs that also accept new line delimited bodies, and for that we have an ND body of T type that also implements the body trait, and this allows us now, it's where T implements the body trait itself, and this allows us now to pass a vector of those types and serialize those new line delimited. So here. Here we're writing new line delimited to the request stream. There are also in the client, which I'm not showing here, but there are also in the client body implementations for string, string slice, and a byte array. So you can pass those also with the client. You can pass those also directly to the client. So that kind of covers everything to do with requests. So you make a request, you get a response back. How do you actually handle that? So that's where you'll be dealing with the response type. Response type has all of the things you might expect to exist on a HTTP response, but they're kind of encapsulated in a type, which is more useful for dealing with Elasticsearch. So we have functions for looking at status code, reading headers. If Elasticsearch has sent back any deprecation warning headers, there's a method for being able to easily read those out. And then there's a couple of functions for reading the response body in different ways. I'm only showing one here. There's one to read it as a string, which is text function, but there's also this one here to read it as JSON. So any type, it will deserialize to a type of B. Any type there just needs to implement SERDES deserialize own type. So in the examples I showed previously, I was deserializing the responses to SERDE JSON value type, but you can define your own types here. So long as they implement deserialized owned, you'll be able to deserialize to those types. So that's kind of an overview of the client crate. But I think it's probably useful to kind of dive into a little bit about how we go about writing and building that client, because the Elasticsearch APIs are, there's a fair few of them now. So sort of hand building a client for all of those things might be quite a cumbersome thing to do. And this is where the API generator crate comes in. So currently the Elasticsearch APIs, there's about 300 of them. And if you were to go and have a look in the Elasticsearch GitHub repository, there's a directory in there that has a collection of REST API specs. Now these REST API specs are JSON documents that essentially define parts of each one of those Elasticsearch APIs. So that they define things like the name of the API, the paths to the API, what methods it supports, get or post, the parts that form part of the URL here, so index and type, and whether those are strings or whether they take a list of strings in this example here. And then they also specify the parameters, so the query string parameters for this search API. And these REST API specs do also say whether the API accepts a request body. There's a few things they don't define though, however. They don't define the actual structure of the request body itself, and they don't define the structure of the response body. They don't define the response HTTP status codes. Those aren't part of the specs currently, at least. But from these REST API specs, we can use those to actually generate large parts of the Rust client, and that's pretty much what we do, and that's what the API generator crate does for us. So it takes the name of the Elasticsearch branch on which the REST API specs live, and it can download those specs, and then it passes all of those JSON specs into a Rust model that represents the entire Elasticsearch API. And then from that API model, so it's like an intermediate API model, from the API model, it can then go and generate all of the Rust code to model all of the parts, all of the builders, all of the function names, all of the documentation. We can generate all of those things from those specs. And how we do that is essentially magic, but if you want to dive into the details of that magic, there's a couple of crates that we make use of in order to do that. So the first one is this is the quote crate. So for those familiar with Rust, Rust has a great macro system where you can write basically meta program and write macros that can feed those to the compiler to generate code at compile time. Quote kind of performs a similar function to macros with some differences, or with some slight differences. One of those being that with quote, you can use it outside of macros or outside of procedural macros, and you can actually take the tokens produced by quote and to string those to get valid Rust code out. So with, by using quote, you can basically meta program parts of the client here inside of this quote macro, and then you can to string that and get Rust code out the other end of it. So everything that you see here with a hash in front of it is going to be interpolated by the quote macro. So in other parts, as we're going and building up the client here, we can build up something to represent the doc. We can then pass it into this macro, and we can build up something to represent the parts enum for this API. And we can build up something to represent the builder name and all the fields of the builder here. And then we can pass them into this quote macro and emit out Rust code, or get a string of Rust code out and then write it to file. So the other part of the equation here, along with quote, is another crate by the same person called the syn crate. So that basically provides us all of the syntax types for the Rust syntax. So the quote macro here is able to take syn types inside of it, so you can build up syn types in code. Like here, for example, we're building up a what are we building up here? We're building up a pattern, a path, sorry, an immutable path, an identity to one. Yes, okay, yeah. So yeah, we're building up the collection of patterns for the parameters that are going to form part of that part of a builder struct. So then we can pass that to the quote crate. We can to string that quote crate, and we can get Rust code out of the end of it. But what we do get out of using syn and quote is just one continuous long string of Rust code with no spaces in it, which if we're going to write that to file, it will certainly compile, and we can certainly build a client that way. But it's maybe a little bit nicer to kind of format the Rust code a little bit before we save it to disk. So we can take a dependency on the Rust format crate and use that to just format the code before we write it to disk. And that's essentially what we do here. We get a bunch of code from to stringing our quote tokens, and then we pass it into Rust format, and we can get some nicely formatted Rust code out there that we can then go and save to a file. So the majority of the client that you see, so if we just jump back in here, and we're in the Elasticsearch directory here, we just jump down into source, and for example, look into this generated folder here, which is where everything from the API generator is put. And we have a look in this root Rust file here. And you just scroll to the top. Everything that we see here is generated from that API generator crate. So you can see the bulk parts enum here and all of the enum variants. How we build up a URL based on whether we're dealing with the none variant or the index variant or the index type variant. So how we build up a URL and percent encode the values that are provided to us. We generate out the bulk builder struct here. So these are all of the properties, and bulk obviously takes a body, a request body, but these are all the query string parameters that bulk can also accept. So everything that you see here is entirely generated from that REST API spec. So it's one way that we can quite easily keep the client in sync with changes that are happening in Elasticsearch, is that we simply point it to a new branch, regenerate the client, and we can push out a new client release at that point. Let's jump back to here. So covered the client, covered how we go about generating the client. So large parts of it are generated. There are some parts which aren't generated, and those will probably grow over time as we start considering and looking at request and response types. But yeah, so the next part that we want to have a look at is the final package that's in the repository, which is this YAML test runner. So it's kind of no good writing a client if you aren't actually testing it and ensuring that it works and does what you expect it to. So each one of the official clients implements a test runner. And so that test runner is able to take YAML tests, which live in another directory in the Elasticsearch GitHub repository, and able to take those test files, which are defined in like a domain-specific language, but they're defined in YAML format using YAML. It's able to take those and compile them or generate in some way API calls using the particular client, and then make assertions on the responses. So those YAML tests at the moment, they're around 1,600, and they test all parts of the OSS distribution and the default distributions, all of the XPack APIs. They might define like a setup call here. So like with the client, call the indices create method with a test index, and this is the body that you need to send. And then here's a method, here's a test defined here that makes a call to the indices get alias API, passing in this name here, so a couple of different alias names, and then it makes some assertions on the response here. So it asserts that the test property aliases, test alias on the response is an empty JSON object, and make some other assertions there as well. So each one of the clients currently can take these specs, generate something specific for their client, and make assertions there to ensure that their client is working correctly. So that's something similar that we do for the Rust client. So we take a similar kind of approach to the API generator and the REST API specs with the YAML tests. So we point out a particular branch. First of all, we download the REST specs, and we need those because we need the REST specs because we need to build that API model for representing all of the Elasticsearch APIs, because we're going to need that model then to go and determine how we generate calls to the client. So we'll download the REST specs, we'll build the API model, then we'll download the YAML tests for the same specific branch, and then we'll use the API model in conjunction with the YAML test to generate integration tests for the Rust client out at the end. And so as an example, if we just jump back here, this get aliases, wildcard, and inclusion test here ends up generating a test like this for the Rust client. So Yeah, so we get a client, do some general setup, then do the specific setup that was in the YAML test. Then we make that call to indices get alias, passing in a couple of alias names. And then we read the response, we get the method, status code, JSON out, and then we make some assertions on the JSON response. So, and if we want to run that ourselves with the client, we can certainly do that. I don't know how well this is going to work running over Zoom, but we can certainly give it a go. So I believe I've already generated the tests. So if I was to go and run cargo test, and let's do xpack async search. So we're only going to run the async search tests, and we need to specify that we're going to run it against the test runner package. And then one more thing is that the YAML tests need to be executed synchronously, so one after another. By default, if you run tests with cargo test, then it wants to run them concurrently using a number of threads. So we need to just specify that we're only going to use one test thread. So if we run this now, why did that not work? Yeah, oh, yeah, because I misspelled that one. So if we just run this, we should end up running, let me find them here. Aha, okay. So let me just set a couple of other flags. So a newer version of the Rust format crate. So we're using a nightly crate here. There are some changes in the latest one whereby some environment variables now need to be set before we call it. Hopefully this will disappear in the next nightly version and we will no longer need to do this, but for now, just need to set a couple of environment variables. So if we run this now, we should be running, so async search, we should be running the tests that exist in this file here. Let's just move that down a little bit. So yeah, so this async search function here. So we get the client, do some general setup. We create an index, create another index, create another index, actually index a document, index a few documents by the looks of it, then refresh the indices, and then we perform an async search, performing some aggregations and a query, and then we make some assertions on the response. And if everything goes to plan, and once this is compiled, then we should run those tests. So I think there's one test in there. Yeah, there's just the one test in there. And if we just wanted to have a look to see what while we're waiting for this, just to see what that YAML looked like from which we generated that test, it's this one here. So, yeah, we're still building. Looks like it may almost be done. So yeah, so as so that YAML test runner package is, so yeah, running one test. There's just one test in there, and it passed. Okay, so all of the assertions that made were all correct. So that YAML test runner package is running all the YAML tests, which is about 1,600 of them. The client itself does have a few tests for testing other things like ensuring that parts, when you call parts, the API relative paths that you expect to be built are built. There's tests for the generator. There are also some tests against just like a mock HTTP server that can just return responses for testing things like certificates and authentication details and headers, because we don't really need to run against Elasticsearch for those kind of things. So there are some tests that perform those kind of things in the clients, but the core of the testing right now for the client is covered by those YAML tests, because there's 1,600 of them and they're quite comprehensive. So let's just jump back into here. So as I mentioned, all of the clients run those YAML tests, and if you are interested in seeing the results of those tests or looking at what is happening with those, client ci.elastic.co is where all of those clients run their tests. You can see at the moment there is a tab missing here for Rust. There should be one there later this week for the Rust client to start running those tests on client CI as well. So that's kind of a rundown of what exists in the GitHub repository, getting started with the client, some of the internals of the client, how we go about building the client from using the API generator project from the REST API specs, and how we go about testing the client using the YAML tests. So what does the future look like for this client? Well, there's a few things I think we need to cover before we can kind of call this client GA. So right now the client is still in an alpha state. One of those things was we needed to have a YAML test runner for it. That is now done. There are a few other things, though, that do need to also be completed before we can say, yeah, we're confident enough to say that this is ready for general release. Some of those things are retries and back off and failover. So the official clients, depending on certain HTTP status code responses, may perform retries on specific responses, or if they're using connection pools that have a collection of connections to multiple different nodes within a cluster, they might fail over to performing a failed request against another node in the cluster. These are things that the Rust client doesn't currently have, but would need to have in order for us to consider it GA. A couple other things as well. All of the clients have a notion of helpers in some form or another. They take different forms depending on the idioms of the language in which they're implemented, but they may take the form of something to help you index a large collection of documents, for example, and those documents may be coming from streamed from file, or maybe they're constructed in code themselves. But they have some way of being able to index, millions of documents by calling this bulk API helper. And similarly, if you want to scroll through all of the documents in Elasticsearch, a client will have a scroll helper to help you do that. So those things also need to be implemented. Down the bottom there, I've put future. So I don't think this is necessarily something that's needed for GA. But in the future, considering the great type system that Rust has, it would be nice to have request and response types to model all of the APIs that are available in Elasticsearch. So there's a project going on at the moment to build a more general solution to solving request and response for all of the official clients. So it's very likely once that project reaches a stage where it's mature enough to be able to use with the Rust client, we would likely be using that to explore building request and response types for the Rust client. So that's kind of what the future of the client looks like. More than happy to always take contributions to it. If you're interested in dipping your toes in Rust, no matter how big or small a thing is that you're interested in doing, more than happy to accept contributions to the client. There are a few open issues there at the moment. I think I generally tag ones which I consider good first issues as good first issues, but there are ones there for the API helpers and a couple other things that I think are needed for GA. So if you see something of interest there and you think, hey, I'm interested in taking a stab at that, then yeah, please reach out on GitHub, and yeah, we can take it from there. That is everything I have for the client. Happy to take questions, to talk about anything related to the client, or explain anything if anything was unclear. But yeah, thank you for your time.
I do have one question that is in general for the clients. Is there some sort of unified TLS handling or SSL TLS configuration, or is every client doing it by itself? Because coming from the Java world, this is usually rather painful. I'm just wondering if there's some sort of generic setup or anything like that nowadays, which this client adheres to as well.
That's a really, really good question. So all of the clients generally will use an SSL or TLS abstraction in their language ecosystem. So some of the kind of nature and behavior for how those things work are going to be dependent on how they're implemented in that abstraction layer. So for example, in the Rust client, there's kind of two very popular TLS implementations. One of them is called, or I should say packages. One of them is native TLS, which is what the client uses by default. And that is essentially a wrapper on top of OpenSSL on macOS and Linux, and a wrapper over S-channel on Windows. Sort of going on from that, sort of going back to kind of some of the quirks, there are differences between how S-channel and OpenSSL work there, some of which native SSL does seem to kind of sort of manage as best as it can, but there do also still seem to be some differences there. So you can be very much, the behavior of those things can be sort of very much dependent on what the underlying components are going to end up doing there. The other popular TLS package in Rust is something called Rust TLS, which is an implementation entirely, an SSL implementation entirely in Rust. So it's very popular because it's a lot more portable than using OpenSSL or using native TLS. And again, that has differences in how it works compared to native TLS. So I think it's fair to say it's a similar sort of situation in the other clients happens as well. They're kind of dependent on the complexities or the behavior of the abstraction on top of the underlying OS TLS library for how those things work. But I think it's fair to say that on top of those language TLS implementations, the clients do try and have common kind of behavior for how TLS actually works. So, for example, let's just jump into the Rust client. Let's get rid of this one. So let's have a look at cert validation. So in the Rust client here, you can define how sort of TLS is handled in the Rust client by using, so let's scroll down a little bit, by using certificate validation. So jumping back to what I was talking about before with the transport builder. So if you want to build a transport to use with the client, one of the functions on there is to define how certificates are handled. So if you making a connection, a HTTPS connection, so a secure connection to a cluster, by default, it's just going to use the underlying, so by default, it's going to use native TLS, and by default, that's going to use the underlying OpenSSL or S-channel to perform, TLS handoff, verify host name, ensure it's signed by a CA that it knows about, etc., etc. But if you wanted to do other things like, say, perform any certificate validation, so for example, say, ensure it's signed by a CA that you know about, but you don't necessarily want to validate the host name, then you can perform that certificate validation here. And if you really want to fly blind, you can turn off certificate validation altogether if you want, which is useful to do for development. So these kind of settings, this kind of full certificate validation or no validation for TLS, those are common abstractions across all of the clients. So we try and build those things to work similarly across the clients. Does that sort of answer the question?
Yeah, absolutely. Thanks a ton. So I've opened up the microphones for everyone. If you want to ask a question, you can go ahead now. Just as a side note, we're gonna have this meetup recorded, and I will put it online on YouTube as soon as I've cut the beginning and end together. So if you want to take a look at the meetup later on, feel free to do so. And yeah, are there any questions? I mean, we are already a bit over the hour, but I just hope Russ has a couple of additional minutes, so I think that's probably fine. So yeah, if you have a question, just unmute now. If you don't, yeah, we have a couple of further meetups coming up at community.elastic.co, so if you want to check those out, go ahead. Russ just put the current Elasticsearch crate for Rust on the screen, so I suppose you just have to search for Elasticsearch on the Rust crate index and you're going to find it.
Yeah, so if you go to crates.io and Elasticsearch, so if you're here and you want to have a read of the documentation, so the documentation is on docs.rs, and this provides you fairly, I would say this is a more comprehensive overview than what you'll find on the GitHub repository. So you have all of the modules here. If you click on async search, for example, you'll get the structs that are available there, the enums, a little bit of detail about what async search does. If you click on any of these links, they should hopefully go to the Elasticsearch docs. So similarly, if we click on async search submit API, it should go to the actual submit async search API, and that gives you some more details there for what this API expects and some of the parameters to the API. So it's quite a good way of exploring the client. Yeah, to kind of get more familiar with it.
Thank you, everyone, and see you next time.